Have you ever wondered how powerful a hydrogen bomb could be, and what makes it so dangerous? Picture this. A single device with the capacity to unleash energy magnitudes greater than the atomic bombs that ended World War II. That's the staggering power of a hydrogen bomb. It's a weapon that can devastate entire cities and change the course of history in a blink. Yet, the power of a hydrogen bomb isn't just about its explosive might. It's about the intricate science behind it, the delicate dance of atoms and subatomic particles that result in this cataclysmic release of energy. You see, the hydrogen bomb isn't just a weapon, it's a testament to the sheer power and potential danger of nuclear physics when pushed to its limits. So, how does this incredibly powerful weapon work? Let's delve deeper into the science behind it. The birth of a hydrogen bomb is a process of intricate scientific manipulation. It's not just about combining elements and hoping for a reaction. It's about understanding the complexities of nuclear fusion, the process that powers a hydrogen bomb. This process, in simple terms, is the joining of small atomic nuclei to form a larger nucleus, releasing a staggering amount of energy. Now, what are the main players in the act? We're talking about hydrogen isotopes, deuterium and tritium. These aren't your everyday hydrogen atoms. Deuterium, for instance, is a stable isotope of hydrogen with a nucleus containing one proton and one neutron. Tritium, on the other hand, is a radioactive isotope with two neutrons. The fusion of these isotopes under extreme conditions is what unleashes the terrifying power of a hydrogen bomb. But how does nuclear fusion occur within a hydrogen bomb? It's all about pressure and temperature. In order to trigger fusion, extreme conditions are required. It's not as simple as flipping a switch or pressing a button. The process is more akin to a cosmic dance, a journey that begins with a smaller atomic bomb. Yes, you heard it right, an atomic bomb, but not to cause destruction. Instead, this explosion serves as the catalyst for the fusion process. The atomic bomb, or more precisely the fission bomb, is used to create the necessary conditions for fusion. It's like lighting a match to start a bonfire, but on a much more enormous and complex scale. Now let's delve a bit deeper into this process. When the atomic bomb is detonated, it generates an incredibly intense burst of X-rays. These X-rays are not your everyday medical imaging kind of X-rays. They are immensely powerful, and they play a crucial role in triggering fusion. Here's how. The X-rays from the atomic explosion engulf the fusion fuel, which is typically a mixture of isotopes of hydrogen. This leads to a rapid and extreme compression of the fusion fuel. It's like squeezing a sponge, but in this case, the sponge is a lump of hydrogen isotopes, and the hand doing the squeezing is a wave of energy from an atomic explosion. This intense compression raises the temperature and pressure of the fusion fuel to astronomical levels, similar to conditions found in the core of the sun. Under such extreme conditions, the nuclei of the hydrogen isotopes overcome their natural repulsion and merge together, a process known as nuclear fusion. And then the magic, or rather the physics, happens. The resulting fusion releases an immense amount of energy. We're talking about a release of energy that dwarfs the initial atomic explosion. This is the power that fuels the stars, harnessed in a hydrogen bomb. But hold on to your hats, because we're not done yet. The fusion process has just begun, and there's still a lot more to come. But what happens next? Once fusion begins, the energy unleashed is beyond imagination. The heart of the hydrogen bomb, where the fusion of deuterium and tritium takes place, is a veritable powerhouse. When these two heavy forms of hydrogen come together under immense heat and pressure, they form a new substance, helium. But this isn't just a simple matter of combining elements. No, it's a process that fundamentally alters the nature of the atoms themselves. You see, the fusion of deuterium and tritium doesn't just produce helium, it also releases a neutron. This might not sound like much, but it's this neutron that carries the real punch. Because in the process of fusion, a tiny amount of mass is lost. And this lost mass isn't simply disappearing. Instead, it's transformed, according to Einstein's famous equation E=mc², into pure energy. And we're not talking about a small amount of energy here. A single gram of fusion fuel can release more energy than 10,000 kilograms of TNT. That's more than enough to level a city. And remember, we're talking about a hydrogen bomb here. The amount of fusion fuel in one of these devices can be hundreds or even thousands of times greater than a single gram. But how does this energy become destructive? Well, the energy released in the fusion process is primarily in the form of kinetic energy of the helium and the neutron. This energy is then transferred to the surrounding bomb material, causing it to heat up and expand rapidly. And it's this rapid expansion that creates the shock wave responsible for the majority of the bomb's destructive power. The heat and light produced in the process also contribute to the bomb's destructive force, incinerating everything in their path and causing devastating thermal burns and fires. This is the devastating power of a hydrogen bomb. But what makes it so dangerous? The dangers of hydrogen bombs go beyond their explosion. Imagine this, a blinding flash, brighter than 1,000 suns, followed by a massive blast wave. This is the immediate impact of a hydrogen bomb detonation. Buildings crumble like sandcastles, and anything in the direct line of the blast is instantly vaporized. The shockwave can shatter glass miles away, while the intense heat can cause third-degree burns, even from a considerable distance. But this is just the beginning. The real terror of a hydrogen bomb lies in its aftermath. The explosion releases a deadly cocktail of radioactive particles known as fallout. This invisible killer descends slowly from the sky, contaminating everything it touches. People, animals, plants, water, soil, nothing is safe. Exposure to fallout can cause severe radiation sickness, leading to a slow and painful death. Even survivors of the initial explosion and fallout are not safe. The radiation can cause genetic mutations, leading to birth defects in future generations. It's a grim legacy that can last for decades, even centuries. And let's not forget about the environmental damage. The intense heat can start wildfires, turning vast areas of greenery into charred wastelands. The shockwave can trigger tsunamis if the bomb is detonated underwater, causing widespread flooding and destruction. Moreover, the fallout can contaminate the soil, making it unfit for farming. And when it enters the water supply, it can poison entire ecosystems. The radioactive particles can also rise up into the stratosphere where they can stay for years, blocking sunlight and causing a nuclear winter. In short, the dangers of a hydrogen bomb are not just immediate and violent, they are also long-lasting and insidious. They can decimate cities, render large areas uninhabitable, and cause untold suffering for generations to come. The power and danger of hydrogen bombs is a stark reminder of the devastating potential of nuclear weapons. So, we've seen how a hydrogen bomb works and how dangerous it can be. Let's take a moment to reflect on our journey through the inner workings of a hydrogen bomb. We started with the birth of a hydrogen bomb, a creation driven by a fusion of scientific curiosity and the grim realities of global politics. The process of fusion, triggered by an initial fission bomb, is the core mechanism that makes it all possible. This is where hydrogen isotopes combine under extreme conditions of heat and pressure, producing helium and an enormous amount of energy. This energy, once unleashed, is what makes the hydrogen bomb so devastating. The blast, the heat, and the radiation. They all contribute to the immense destruction a single hydrogen bomb can cause. But it's not just about the immediate devastation. The long-term effects of radiation can linger for years, causing health problems and environmental damage that can last for generations. And that brings us to the dangers of a hydrogen bomb. The immediate and long-term impacts on human life and the environment are staggering. The devastation is not limited to the blast radius. The fallout can spread far and wide, affecting people and ecosystems hundreds or even thousands of miles away. Beyond the scientific and technical aspects, there are also moral and ethical considerations to ponder. The power to unleash such destruction comes with immense responsibility. The decision to use such a weapon can't be taken lightly. It's a decision that weighs heavily on the conscience of the world, a decision that could alter the course of history. While the science behind a hydrogen bomb is fascinating from a theoretical standpoint, it's also a stark reminder of the destructive potential that lies within our grasp. The knowledge we have gained should serve not just to advance our understanding but also to guide us in making ethical decisions about its use. While the science behind a hydrogen bomb is fascinating, it also serves as a reminder of the immense responsibility that comes with such knowledge.